Okay, so in this video for Math 1560 Calculus 1 at U of L for Fall 2017, we're going to look at the general procedure for curve sketching. So we're going to just lay out all of the ingredients that you need to consider when sketching the graph of a function. We'll keep one example with us as we go, and I'm going to I'm not going to work through all of the details in that example. I'm just going to give you the answers just so you kind of see how things go. And after this video, we're going to look at a few concrete examples, and of course, we're going to do more of them in class. Okay, so what's the scenario? The scenario is that somebody has handed you a function. All right, in this case, we've got a rational function, and you want to know what the graph looks like. So there's a lot of information that goes into the graph, figuring out what the graph looks like for your function. First thing you got to do is figure out, okay, where is my function defined? What's the domain? Well, in this case, we might as well say what it is, right? We know that it's everything except for, well, x can't equal plus or minus 3, or else the denominator is 0. So we get some domain information. The intercepts. So the x-intercepts, those are the places where y equals 0. So if we factor the top, we can see that x equals 2, x equals minus 2. Those are going to be my x-intercepts. And maybe we should, let's actually be a little bit more precise here. We could write our intercepts as 2, 0. Minus 2, 0, to be clear that those are the x-intercepts. What's the y-intercept? If x is equal to 0, f of x is going to be minus 4 over 9. Okay, right. What about asymptotes? Well, we get two vertical asymptotes, right? Those are the two places where the function is undefined. So we have asymptotes at x equals 3, at x equals minus 3. What about horizontal asymptotes? Well, we can see that the degree of the top matches the degree of the bottom, and so we know that when we're in that situation, we do the coefficient for the top divided by the coefficient of the bottom, and we see that that's going to give me y equals minus 1 as a horizontal asymptote. Symmetry. So for symmetry, you're looking for, and not every function is going to have symmetry, but you're looking to find out, okay, is my function even or odd? So an even function is one where f of x equals f of minus x, and an odd function is one where f of x equals minus f of minus x. Okay, and this has some implications for what the graph looks like. For an even function, the graph when x is less than 0 is just the mirror image of the graph when x is bigger than 0. You reflect across the y-axis. For odd functions, you actually reflect twice. You reflect first across the y-axis and then across the x-axis to see what the graph looks like when x is less than 0. In this case, we can notice that our function is in fact even, right? If I put minus x in into f of x, it gets squared, so I get the same value for f of minus x that I get for f of x. And then we got to go on. We got to calculate our critical points, extrema. Well, everything else on this list, we're going to need derivatives, right? We're going to need either the first derivative or the second derivative. So we're making some progress. Okay. We've got these bits for the original function, right? X-intercepts and the y-intercept, we saw that those are 2, 0, minus 2, 0, 0, and minus 4 over 9. We saw that we had two vertical asymptotes, one horizontal, and limits at each asymptote. That's also going to be important, right? Remember how we get the limits at the asymptotes? We know they're going to be either plus infinity or minus infinity. Well, for that we need the sign diagram for f. Okay, so f of x, if you factor it, is x minus 2 times x plus 2 over 3 minus x times 3 plus x. And so it's undefined at minus 3. It's undefined at 3. We have zeros at minus 2 and at 2. And if you work out the signs in each interval, you'll find that the signs go like this: plus, minus, minus, plus, minus, right? So now we know that for the asymptote at minus 3, we know that we're going down to minus infinity on that side, we're going to plus infinity on that side, and similarly here we're going to plus infinity there, minus infinity there, just by looking at those signs in the sign diagram. Okay, we already confirmed that the function is even, so we've got the symmetry taken care of, right? In other cases the function might be odd, so this is something you want to watch out for. You don't have to look for symmetry, but if you notice symmetry, it's going to cut down the amount of work you have to do, because you can just take the graph that you did for x bigger than 0 and copy it to get the graph when x is less than 0. So now you move on to the derivative. Okay, so I'll work out the derivative for you. In this case, you find, with a little bit of work, and I'll leave this as an exercise for you to confirm, you get 10x over 9 minus x squared squared. This is your derivative for the original function. Okay, and so now you can look at the sign diagram. Okay, so the derivative is undefined at minus 3 and 3, right? Those were points that weren't in the domain of our function, so they're not really considered critical points, even though the derivative is undefined there, because f was also undefined there. And we have a 0 at 0, so we do have one critical point at the origin. Okay, and now we check the signs in each interval. Well, the bottom is never negative, right, because of the square, so the only thing that matters is whether x is positive or negative, so we get a sign diagram that looks like that. And we can see that at 0 we go from decreasing to increasing, so we're looking at a minimum there. So we can say that our function is going to be increasing on, well, from 0 to 3, and from 3 to infinity. I'm leaving out 3 because the function is not defined there, so we don't include 3. Okay? And similarly, I'm decreasing from minus infinity to minus 3, and from minus 3 to 0, and I have a critical point. Okay? When x is equal to 0, and remember that when x is equal to 0, we worked that out, that was our y-intercept. Y was equal to minus 4 over 9, and now we can see that because we're going from decreasing to increasing, this is a local minimum. Alright, so that's all the information that we can really extract from the first derivative. Now we want to go on and we want to look at the second derivative. So for the second derivative, we calculate f double prime, and again I'll leave you to fill in the details here. You can confirm that with a bit of work what you get is 3 plus x squared times 30 over 9 minus x squared, and this time the denominator is cubed. Okay, so the numerator is always positive, it never vanishes, right? 3 plus x squared is always bigger than or equal to 3. So the only points that we have to keep track of are the 3 and the minus 3 in the denominator. And here you actually do have to pay some attention, because what you have is, and maybe I'll do this in stick to blue, 30 over 3 plus x squared, and on the bottom I've got 3 minus x cubed, 3 plus x cubed. And so I've got odd powers on the bottom, so I am going to get some sign changes here. when x is bigger than 3, this term is going to be negative. The 3 minus x will be negative. The 3 plus x will be positive. So overall negative. In between it's going to be positive, and then out here both of them are negative, so I get minus plus minus for my sign diagram. Okay, so now I know that my concavity is I'm concave down here, I'm concave up here, I'm concave down here, and there are no inflection points. There was nowhere that the second derivative was 0, so I don't have to worry about inflection points. There are changes in concavity, but they happen at the asymptotes. Okay, so now I can put everything together. If I wanted to actually graph this function, okay, I start plotting things, and so what I do, I draw some axes. The first thing I might put in maybe is my asymptotes. So let's put in those asymptotes at +3 and at -3. And let's start plotting points. We had intercepts at -2, 0 and 2, 0. Those were our x-intercepts. We had a y-intercept at 0 and -4/9. So there, we can mark those. So -2, 0. It's not a bad idea to label your points. And remember that that y-intercept was also a local minimum, so that's of interest for that reason as well. Okay? So those are the only 3 points that we have to plot. The next thing we do is we plot the behavior near the asymptote. So if we jump back, here was our asymptotic behavior, right? Going up on the inside, going down on the outside. So if we put that in, we know that we're looking at something that goes like that. Like that. And now inside, if we look at the first derivative, we can see that, well, we decrease from the vertical asymptote until 0, right? In this region we're decreasing, we hit that minimum at 0, then we start increasing, and so and also notice that we are concave up all the way between the asymptotes. So we know what that has to look like then. We get something that just heads down, passes through the minimum, turns and goes back up, and heads up towards the other asymptote. Okay, now we got to fill out the outside. We also know there's one asymptote I'm missing, right? What am I missing? I'm missing there was a horizontal asymptote at -1. And so how it looks, I'm gonna put it in, and then I'm gonna tell you why it has to be like this. The rest of the